Welcome back to the deep dive. If you were with us last time, you'll know we started looking into intelligent agents, really getting a handle on what agentic AI is all about.
Right, these autonomous systems designed to perceive, think, and then act in their environments.
Exactly. So today, we're building right on that foundation. We're going to sort of pull back the curtain on the agent's mind, its architecture.
The blueprint, essentially.
Yes, the blueprint, how these systems are actually designed to see the world, process what they see, and then, figure out what to do next. It's all about the philosophy behind the AI's behavior.
And understanding these architectural philosophies, it's crucial. It's not just academic. If you want to build effective, reliable, predictable autonomous systems, you need to grasp this.
Absolutely. It's key for innovation, moving from just ideas to actual working agents. So to really give you a full picture, we're structuring this deep dive as a Q&A. We've got a list of core questions we'll tackle one by one.
Okay, sounds like a good plan.
Great. So first we'll outline these questions for you, then we'll just work through them. We'll ask, 1, what's the core cycle all intelligent agents operate on? 2, what actually happens in the perception and action parts of that cycle? 3, what does the planning phase really involve? The thinking part. 4, what's the classical deliberative way to design agents? The planners. 5, and what are the strengths and weaknesses of those planner agents? 6, then what about the alternative? What defines a reactive agent? The doers. 7, what are the pros and cons of that reactive approach? 8, how do hybrid architectures try to get the best of both worlds? 9, can you explain the subsumption architecture as an example? 10, and what's the BDI belief, desire, intention architecture? Sounds interesting. 11, how does the agent's internal model of its world relate to its autonomy? 12, what are the autonomy levels NIST talks about? 13, what is state representation? How does an agent store its knowledge? 14. And finally, we'll summarize the key ideas and trade-offs in agent architectures.
That covers a lot of ground. It really gets to the heart of how these agents are built.
It does. It shows you the strategic thinking behind building any intelligent system, really, from robots to chatbots.
Absolutely.
Okay, so let's dive right in. First question. Could you elaborate on that core cycle, the one all intelligent agents operate on?
Sure. So at its very core, every single intelligent agent, no matter how simple or complex, runs on this continuous loop. You can think of it as its engine.
The engine of its behavior.
Exactly. We often simplify it down to perceive, think, act. But a slightly more refined model, and one that's really useful for understanding architectures, breaks that think part into what we call the planning phase.
Okay.
So the loop becomes perception, planning, action. The agent perceives its environment using sensors. Then it does some kind of planning. Could be simple, could be complex to decide what to do. And then it takes an action using its actuators.
And that action changes things.
Right. That action changes the environment, which of course is then picked up by the perception phase again. And the whole cycle restarts. It's continuous.
Okay. And you mentioned the planning phase is key.
Yes, absolutely key. How that planning phase is designed, what it actually does, that's what fundamentally defines the agent's architecture. That's where the different philosophies really come into play.
Right, that makes perfect sense. A continuous feedback loop. So let's break down the start and end of that loop a bit more. Question 2. What exactly happens during the perception and action phases?
Okay, let's start with perception. This is the input phase. The agent uses its sensors, maybe a camera, a microphone, text input, whatever, to gather raw data from the environment.
Like raw pixel values or sound waves.
Exactly. But raw data isn't usually useful on its own. So perception also involves processing that raw input into something meaningful, something structured that the agent's internal logic can actually work with.
So making sense of the raw input.
Precisely. It could involve things like object recognition in an image, identifying chairs and tables, or speech to text, turning audio into words, or even parsing the grammar of a sentence to understand its meaning. It's about creating actionable information from sensory noise.
Got it. Transforming input into understanding. And then, once it understands, it acts. What about the action phase?
The action phase is the output. It's where the rubber meets the road, so to speak. After the planning phase has chosen what to do, the action phase is simply executing that chosen action.
How does it do that?
Using its actuators. That could be anything from moving a robotic arm, sending an electrical signal to turn on a light. generating text for a chat response or, adjusting the throttle in a self-driving car.
So making a change in the world.
Exactly. The action leads to a change in the environment state. And that change, as we said, is then perceived, starting the whole loop all over again. It's this dynamic interaction that lets agents pursue goals and adapt.
Okay, so perception is the eyes and ears, action is the hands and voice. But that middle part, the planning phase, that sounds like the real brain. Question 3. What does that planning phase involve? It sounds critical.
It really is the cognitive core. Once the agent has this useful, structured information from perception, the planning phase is all about figuring out the next move. And it's usually not just one step.
More involved then?
Yeah, typically a multi-stage process. First, the agent often updates its internal understanding, its world model, with the new information it just perceived. So its beliefs about the world get refreshed.
Okay, update the knowledge.
Then it generates options. Based on its current state, what could it possibly do next? What actions are available to it?
Right. Considers the possibilities.
After that comes evaluation. For each possible action, it tries to predict the likely consequences. What will happen if I do this? It uses its internal model and its goals to figure this out. Will this action get me closer to my objective? Will it maximize some utility function?
Predicting the future, basically.
Well, in a sense, yes, predicting the outcomes of its potential actions. And then finally, selection. Based on those predictions, it chooses the single action that it calculates will be best for achieving its goals or maximizing whatever value it's programmed to seek.
And this can be simple or complex, you said.
Hugely variable. It could be as simple as looking up a rule in a table. If battery low and in your charger, then connect to a charger. Very reactive. Or it could involve incredibly complex multi-step reasoning, like searching through millions or billions of possible future game states in chess or Go, looking many moves ahead.
Wow, okay. That range really highlights the different design choices. Which brings us to question 4. The document mentions 2 main philosophies for designing this planning phase. What's the classical deliberative approach?
Right. The deliberative approach is, well, it's the traditional top-down way of thinking in AI. It really follows that sense, plan, act sequence quite rigidly.
Sense, plan, then act. Emphasis on the plan.
Exactly. These agents rely very heavily on building an explicit, symbolic model of the world. A detailed internal map, you could say, representing objects, properties, relationships, everything it knows.
Like a mental database.
Sort of, yeah. And then they use formal logic, reasoning algorithms, and complex planning techniques to figure out a sequence of actions. The key idea is to generate a complete plan to reach the goal before taking even the first step.
You mentioned chess before. Is that a good example?
Perfect example. A traditional chess AI doesn't just react. It senses the board state. It plans out a multi-move strategy aiming for checkmate, maybe exploring thousands of variations, and then it executes the first move of that chosen plan. That's pure deliberation.
Okay, I can see the power in that. Very rational, very goal-oriented.
Yep.
So, question 5. What are the key strengths and weaknesses of these highly rational planner agents?
Well, the main strength, as you noted, is their potential for optimality. Because they plan so thoroughly, considering many possibilities, they can often find the very best solution to complex problems that require long-term thinking. Think logistics, optimization problems, strategy games.
They can be very smart.
Very smart, yes. But the weaknesses are pretty significant, especially in the real world. First, they're often incredibly slow. All that planning takes a lot of time and computational power.
Right. Thinking takes effort.
Exactly. Second, building and maintaining that perfect symbolic world model. It's extremely difficult, maybe even impossible, for complex dynamic environments. This relates to something called the frame problem in AI.
The frame problem. What's that?
It's the challenge of figuring out what doesn't change when an action occurs. If a robot moves a box, its location changes, fine. But what about the color of the walls, the position of the stars? Representing all the things that stay the same is computationally explosive.
Okay. Maintaining an accurate model is hard.
Very hard, especially when things change unexpectedly. And that leads to the biggest weakness. If the real world changes while the agent is busy making its elaborate plan, the whole plan might become useless before it even starts executing it.
So the plan becomes outdated.
Instantly. They just aren't good at reacting quickly to sudden, unexpected events. They get stuck in their planning loop. Smart but slow and brittle in dynamic situations.
Okay, smart but slow and struggles with change. That definitely sounds like a problem for, say, a robot in a busy factory. Which leads us to question 6. Given those weaknesses, a different philosophy emerged. What defines a reactive agent?
Right. Faced with the brittleness of deliberative agents, researchers, particularly people like Rodney Brooks back in the 1980s, proposed a radical bottom-up alternative, the reactive agent.
Bottom up. How so?
They completely rejected the need for complex internal models and long-term planning. Instead, reactive agents rely on a very tight, direct coupling between perception and action.
Skipping the complex planning.
Essentially, yes.
Mm-hmm.
The idea is to map sensor inputs directly to actuator outputs using a collection of relatively simple, fast rules or behaviors.
Yeah.
If you sense an obstacle, then turn away. If you sense light, then move towards it.
Just immediate stimulus response.
Pretty much. It doesn't build a world model. It doesn't predict the future. It doesn't remember the past in any complex way. It just reacts purely to the current sensory input, the now. Think of insect-level intelligence, perhaps, or that robot vacuum cleaner hitting a wall and instantly changing direction.
That sounds much faster.
Incredibly fast.
So question 7. What are the pros and cons of this reactive doer approach?
The big advantages are speed, robustness, and low computational cost. They react almost instantly because there's no complex deliberation. This makes them really good at navigating dynamic, unpredictable environments because they're always responding to the latest information.
Good for surviving in chaos.
Excellent for it, yes. They're often cheap to build and run. But the weaknesses are the flip side. They only display what we call emergent intelligence. Complex-seeming behaviors can arise from the interaction of simple rules, but they can't actually plan ahead.
So they can get stuck.
Easily. They can fall into simple traps or get stuck in repetitive loops because they lack any foresight or memory of where they've been. They have no explicit goals. They can't reason about abstract concepts or complex problems.
And their behavior might be hard to predict.
Sometimes, yes. Because it's just the sequence of immediate reactions, it can occasionally lead to unexpected overall behavior. So it really highlights that core trade-off. Deliberative is smart but slow. Reactive is fast but simple.
Okay, that's a really clear distinction. Smart but slow versus fast but simple. Neither seems ideal for all situations. Which brings us neatly to question 8. It seems there's a trade-off. How do hybrid architectures attempt to solve this?
Exactly that. It became pretty clear that neither pure approach was the silver bullet for general-purpose intelligence, especially for agents needing to operate robustly in the real world. So the natural step was to try and combine them.
Get the best of both worlds.
That's the goal. Hybrid architectures aim to integrate the speed and robustness of reactive control with the goal-directedness and foresight of deliberative planning. They try to get quick reactions when needed, but also allow for thoughtful planning when time permits.
How do they typically do that?
Often using layered architectures. You might have different layers or modules within the agent, some handling immediate reactions, others handling more abstract, long-term reasoning, and mechanisms for them to interact.
Interesting. Layering the capabilities. Can you give us an example? Let's move to question 9. Could you explain the subsumption architecture as an example of a hybrid model?
Absolutely. Subsumption, developed by Rodney Brooks, who also championed reactive systems, is a classic and very influential early hybrid architecture, especially in robotics.
Okay, how does it work?
It structures the agent's behavior into a hierarchy of layers. Each layer implements a specific competence or behavior, and they operate largely independently and in parallel.
Like different skills.
Exactly. So the lowest layer might be something very basic and reactive, like avoid obstacles. The next layer up could be wander around. A higher layer might be explore, and an even higher one, go to recharge station.
So layers of increasing complexity.
Right. Now the key idea is subsumption. Higher layers can inhibit or suppress the outputs of lower layers.
They can override the lower levels.
Precisely.
Yeah.
So the robot might be happily executing its wander-around behavior, but if the lowest avoid obstacles layer suddenly detects an imminent collision, its output takes precedence. It inhibits the wandering output and makes the robot turn or stop immediately.
So it gets the fast reaction when needed.
But it can still pursue higher-level goals like exploring or recharging when the coast is clear. It allows for immediate life-saving reflexes while still enabling more deliberate, goal-oriented behavior. It's a very elegant way to blend reactivity and purpose.
That's a clever design. Okay, let's move to another type. Question 10. What is the BDI, or belief, desire, intention architecture? It sounds more abstract, maybe more human.
It does, doesn't it? BDI is a very powerful and popular architecture, especially in areas like multi-agent systems or where agents need to interact naturally with humans. It models the agent's internal state using concepts that are deliberately analogous to human mental states.
Beliefs, desires, intentions. Like us.
Kind of, yes. Let's break it down. First, beliefs. These are the agent's information about the world. Crucially, just like our beliefs, they can be incomplete, uncertain, or even flat out wrong. An agent might believe a door is unlocked, but it might be mistaken.
Okay, it's knowledge, potentially flawed.
Then, desires. These are the agent's objectives or goals. What states of the world does it want to achieve? An agent might have multiple desires, maybe even conflicting ones, like wanting to explore but also wanting to conserve energy.
It's motivations.
Right. And finally, intentions. Intentions are the desires that the agent has actually committed to achieving right now. It has chosen a desire, maybe formulated a plan to achieve it, and adopted it as its current active goal.
So the chosen active goal.
Exactly. If the agent desires to be outside, believes the door is unlocked, and decides this is the priority, it might form the intention. I intend to go through the door using plan A.
And how does this work in the loop?
It provides a really practical reasoning cycle. The agent perceives the world, updates its beliefs, it considers its desires in light of its beliefs, what's achievable, what's important. It then selects some desires to become intentions. And finally, it executes the plan associated with its current intentions.
So it's constantly reconsidering.
Yes, that's the key. It allows the agent to be goal-directed and proactive by forming and pursuing intentions, but also responsive. If its beliefs change drastically, for example, it perceives the door is now locked, it can drop its current intention and perhaps form a new one, like finding a key. It balances commitment with adaptability.
That sounds very flexible and powerful. Okay, shifting gears slightly, let's talk about how the agent sees the world internally. Question 11. How does an agent's internal environment model relate to its level of autonomy?
That's a really fundamental link. The internal environment model is basically the agent's worldview. It's representation of how the world works, how its own actions affect that world, and maybe even how the world might change independently.
Its understanding of reality.
Precisely. And the sophistication of that model is directly, and I mean directly, tied to how autonomous the agent can be.
More understanding equals more freedom.
In essence, yes. A simple reactive agent, as we discussed, might have almost no internal model beyond its immediate sensory input. Its autonomy is therefore very low, it just reacts.
Right.
But an agent with a more sophisticated model, one that can predict the consequences of actions, maybe even reason about the goals of other agents, that agent can achieve much higher levels of autonomy. It can formulate long-term plans, adapt to changing circumstances without needing constant guidance, and make more complex decisions independently.
So the model enables planning and independence.
Exactly. The quality, accuracy, and predictive power of that internal model are what allow an agent to act effectively and safely on its own. You can't have high autonomy without a good grasp of your environment and the effects of your actions.
That makes sense. And speaking of autonomy levels, question 12, the document mentions a hierarchy proposed by NIST, the U.S. National Institute of Standards and Technology. What are those levels?
Yes, NIST provides a really useful framework for thinking about and classifying autonomy, especially in systems where humans and AI interact. They propose 3 main levels.
Okay, what's the first one?
First is human in the loop. Here, the AI might analyze data, suggest options, provide recommendations, but the human always makes the final decision and executes the action. The AI is an advisor.
Like a decision support tool.
Exactly. Think of a medical diagnosis system suggesting possibilities, but the doctor makes the final call.
Okay, level 2.
Second is human on the loop. In this case, the AI can act autonomously. It can make decisions and execute actions on its own. However, there's a human supervisor actively monitoring its performance who can step in, override its decisions, or take control if needed.
Like a pilot monitoring an autopilot.
That's a perfect analogy. The system runs itself, but the human is ready to intervene.
And the third level.
Third is human out of the loop. This is the highest level. The AI operates fully autonomously for its designated tasks without any requirement for human monitoring or intervention during its normal operation. It makes its own decisions and acts on them completely independently.
True autonomy.
Yes, this is where you see highly advanced AI in specific, often well-defined or safety-critical domains designed to function without direct human oversight.
That's a very clear progression. Okay, let's go back inside the agent's head. Question 13. What is state representation? And what are the different ways an agent can represent its world internally? We touched on models, but how is the information actually stored?
Right. State representation is about the specific data structures the agent uses to encode its beliefs, its internal model,
Yeah.
how it actually stores what it knows. And this choice is fundamental because it dictates what the agent can reason about.
The format matters.
Absolutely. There are three main types commonly discussed. First, atomic representation. This is the simplest. The entire state of the world is represented as a single, indivisible unit or label. Like the state is just in kitchen or charging.
Very basic.
Very basic. Easy to work with, but lacks detail. You don't know why you're in the kitchen or how much charge you have.
Okay, what's next?
Second, factored representation. This is much more common and powerful. The state is broken down into a fixed set of variables or attributes, each having a value. So instead of just in kitchen, you might have location kitchen, battery 75%, time 14.30 is raining false.
Like a database record for the current state.
Exactly. This structured format allows for much more sophisticated reasoning because you can reason about individual attributes and their relationships. Most modern AI uses some form of factored representation.
And the third type.
Third is structured representation. This is the richest and most complex. Here, the state isn't just a set of variables, but a collection of objects and the relationships between them, often represented using logic or graphs.
Like?
For example, on Table 1, Book 2, Color Book 2 Red, adjacent Roomba, holding RoboArm Cup 3. This allows for very complex relational reasoning, understanding how different objects connect and interact. It's common in classical AI planning and knowledge representation, like in the semantic web.
So atomic, factored, structured, increasing complexity in detail.
Precisely. And the choice directly impacts the kind of reasoning possible. Atomic might just allow simple lookups. Factored enables things like constraint satisfaction or Bayesian networks. Structured allows for complex logical inference, planning with relationships, and deeper understanding.
This has been incredibly thorough. We've gone from the basic loop to complex internal representations. So question 14 to wrap this up. What are the core concepts and trade-offs we should really take away from this deep dive on intelligent agent architectures?
I think the absolute core concept is that the architecture is the agent's blueprint. It's the fundamental design choice that connects how an agent perceives the world to what it ultimately does.
Perception to action via the architecture.
Exactly. And the biggest trade-off we kept seeing is that tension between the deliberative approach, smart, capable of complex planning but potentially slow and brittle, and the reactive approach, fast, robust, computationally cheap, but simple and lacking foresight.
The smart but slow versus fast but simple dilemma.
Right. And we saw how modern AI often tries to bridge this gap with hybrid architectures like Subsumption or BDI, aiming for both responsiveness and intelligence. They try to layer or integrate these capabilities.
Getting the best of both.
Trying to, yes. So the ultimate takeaway is that designing an agent architecture isn't about finding the one perfect design. It doesn't exist. It's a masterclass in trade-offs.
Depends on the job.
Completely. The best architecture depends entirely on the specific task the agent needs to perform, the kind of environment it will operate in. Is it static, dynamic, predictable? And what performance metrics really matter? Is speed critical? Is optimality essential? Is robustness paramount? It's always a strategic balancing act.
What a fantastic summary. We've really covered the journey, haven't we? From that basic perception planning action cycle through the deep differences between reactive doers and deliberative planners and into hybrid systems like subsumption and BDI. And it's become so clear how crucial that internal environment model and the state representation are. They really define the agent's potential, its intelligence, its reasoning power, and ultimately how autonomous it can truly be.
Absolutely. The architecture dictates the capability.
It really is about balancing those different needs, a strategic decision, like you said.
Indeed. And these architectural blueprints, they set the stage. They provide the structure.
Perfect lead-in, because that's exactly where we're going next time. In our next deep dive, we'll look at how these architectures are actually implemented. We'll explore planning and goal-oriented behavior.
Getting into the algorithms and techniques.
Exactly. How do agents actually create and follow those plans within these frameworks? We'll look at search algorithms, decision-making under uncertainty, and how machine learning fits into bringing these blueprints to life.
That sounds fascinating, definitely building on today's foundation.
Should be great. So definitely tune in for that. For now, a huge thank you for joining us on this deep dive into intelligent agent architectures.
My pleasure.
If you found this helpful and want to keep exploring AI with us, please do subscribe to our channel, Tech AI and Beyond. We'd love to have you with us for the next part of the journey. Thanks for listening, and we'll see you next time.